Okay, so my name is Vesa Karmonen, in case you haven't read the slide yet. And I'm going to talk about a simple pattern matcher implementation in JavaScript that I did in the previous project that I worked on. So this is, again, one of my favorite quotes. It's possible to make the structure of the program match the structure of the problem being solved. And that's kind of what pattern matching is all about. What you want to do with pattern matching is that you have some sort of data structure and you want to match something from the data structure, maybe transform it to something different. And with pattern matching, you can actually make the matcher have the same structure as the data being matched. Also, this is not really anything fancy, so it's very simple, basic functional programming, and I think that pretty much any functional programmer should be able to do this kind of stuff. Maybe not have the same kind of opportunity in every project to do this, but if you have, then definitely go for it. So what's the context for this? Basically, we had this old JSON-based format for exams, and it has a lot of problems, like it's missing a lot of data, it has kind of messy structure, and one of the funny things is that when it's actually rendered, then stuff is often rearranged in the DOM, so the structure in the JSON doesn't necessarily match the structure of the real exam. So what kind of data do these things have? So I have an example here. Let's make it a little bit bigger. So this is actually the JSON data structure, the original data structure, and this basically describes an exam. So there's the title of the exam, then there are various texts which actually contain HTML, which is one of the bigger problems in this. Also, there are lots of like manually written IDs here that have to be written correctly when doing this matriculation examinations, and so on. And then there's lots of data missing from here. Like there should be like classifications for these questions and other kinds of information here, but it's missing. And what we actually would like to do is to sorry, it's wrong. Here's the more interesting example. Here's like a more complex structure, which is actually XML, which is transformed to JSON. So you can see that there are like nodes with some element type, and they have this tag type also, and also children. So this is basically XML as JSON, and as you can see, it's quite. It looks rather verbose when it's rendered like as JSON like this, but as XML, it's actually much more readable, and it has the benefit, for instance, that styling and the HTML structure can be represented there directly, so it's no longer in the text there, and it's also sort of easier to edit and visualize like that in XML form. So so basically what the problem is that we need to be able to produce that XML from our old exams, and the problem is that where do we get the data from? And we cannot just use JSON because there's often like custom code in the exams that rearranges the data. And one of the ideas was that we could extract the structure from the rendered HTML and then transform that to the XML that we want, and then add additional information to the XML, like information missing from it, like scores for the questions and so on. But the problem then is that how do we use HTML structure or XML structure in JavaScript? So as you saw previously, the data structure is quite complex, so it can be tedious to manipulating JavaScript. So the idea, well, basically this started like Mikko was working on this, and he came to me and asked something like, would there be some sort of lens for doing this kind of thing? And I thought about it for a moment and thought that lenses are probably not the best approach to this. I think that something based on pattern matching would be better. So the idea that I had was to basically do something similar to what Neil Mitchell describes doing in his paper on the Uniplate library, which is basically a Haskell library from something like a decade ago, where he creates this library for doing generic transformations on compiler intermediate data structures, basically trees, stuff like that. So if you look at the paper just briefly, so this is the paper. I recommend to read this paper. This is quite easy to read and can be quite fun, even if it's a little bit dated. I think that nowadays there are better techniques for doing many of these things. But the basic idea presented here is that we have this kind of transformation rules, and we have the data structure for those expressions somewhere. Not sure if it's here's like the data structure for those expressions, and in the compiler you have complex trees of expressions, and then you use this Uniplate library for doing transformations like simplifying expressions. For instance, this would transform sub-expressions to a combination of addition and negation, and this replaces addition when both arguments are the same with multiplication by 2. So you can do this kind of transformations, and you can do them to the whole abstract syntax tree of the program by using a kind of bottom-up transformation on the data structure, and you repeat that transformation until sort of a fixed point is reached. So if first you make some sort of transformation, then you check again whether there's more stuff to transform in the data structure, and then you're using those pattern matching rules there. So what we're basically kind of going for, what is the ultimate result here, is that we want to be able to describe rules like this. This is like a rule from the actual converter that converts the HTML structure to the XML structure. So this kind of matches a certain kind of structure from the HTML and then outputs another kind of structure. And this part here is basically the pattern that matches the HTML structure, and here we have the this is actually like a function call to a function that produces this kind of XML structure from the code from the data. It's as you can see, it's complex enough that you probably don't understand exactly what it's doing right now, but if you would imagine writing code by hand that matches the same kind of information from the HTML structure, then you could imagine it would involve a lot of if statements. So this is much more compact way of doing the same and more visual. You can see that it matches some sort of node which has the question text classes, and it has these kind of children where the first child has this question text class, and then it has children where there's like a question number class, and then there's one child which can be one of these 4 different forms. There's like an OR pattern here, and also there's like an AND pattern here that matches the title. So we can do all kinds of complex pattern matching. This ellipsis form matches any number of nodes. So if this would be missing, then it would match only a children list with exactly one element. And sorry about that, I have a little bit of flu, so it seems like my voice is going out all the time. So first the trivial bits. I mentioned that we're doing this kind of a bottom-up transformation. So here's actually the whole implementation of bottom-up transformation. So if you look at the code, then basically to do this bottom-up transformation on some data structure X with some function, we just first we basically map the children of x, and after we've mapped the children of x, then we actually use the function on the node itself. So, and to map children, we look at if we are actually dealing with an object, and if we are, then we actually map the object, whether it's an array or object, and if it's not, then we just return it because it doesn't have any children. So what this looks like in reality. So can everyone read this code? Mm-hmm. Okay. So so here's like a very simple data structure. This is just some random JSON that I came up with. So basically an array of an object that has another array, and then there's like an object and another object and some elements. That's just some random made up data. So what I'm doing now here is that for everything that the bottom-up transformation looks at, I'll just console log the data at that point and return the data as is. So what we can see here is that it works bottom up. So the number 1 here is a leaf from this data structure, and from that 1 upwards there is this object with the y, and then there are these 2 and 3 are also leaves, and then this array contains those 2 and 3, and then then there's this object with z, and then there's the array, and so on. So basically it works from the leaves of the data structure upwards and tries to do something to each of those nodes. And in this case we are just logging the data so that we can see that the order in which those leaves are actually, or these parts of the tree are actually processed. So we could do transformations. So for instance, we could like wrap every object or every value that we get to the mapping function as an array. So we can see that the leaves number 3 and number 2 are now wrapped inside arrays, and so is the number 1 here, and also the object with the y is also wrapped inside an array, and so on. So every part of the data structure is now wrapped in an extra array. These are just like random examples to understand what this bottom-up transformation means. So here's another one. This looks at the data, and if it's an array, then it reverses the array, and otherwise it just returns the data as is. So we have this array here, and then this array here that contain more than 1 element. So we can see that the numbers 3 and 2 are swapped, and also the object with y is now the second element in the array rather than the first one. If you have any questions, then please ask them away. Also, here's another example. We look at every object, and then if it's a number, then we negate it, and otherwise we return it as is. So all the numbers in the data structure are now negated, basically. So with just these 2 lines of code, we can sort of define this whole data structure bottom-up transformation. All clear? All right, cool.
Mä otan lisää nuuskoa.
Right. So I mentioned that we want to do the transformation to fixed point. So what's this fixed point? Fixed point is basically like a point in a mathematical function where if you apply the function to some value x, then actually the function returns the same value x. So for instance, if you have like the power to the power of 2 function, and then it has 2 fixed points, 0 and 1. So if you multiply 0 by 0, you get 0, and if you multiply 1 by 1, you get 1. So those are like fixed points. But in this case, of course, we are not dealing with numbers, we are dealing with tree structures. So how do we transform something to a fixed point? So we have this function that we want to apply to everything in the tree structure, and we have the tree structure, and then we go bottom up in the tree structure, and for everything in the tree structure we apply the function, and it gives us some value y back. And now if the x and y are now equal, like the original value at that point in the tree is equal to the value returned by the function, then we just return the original value from from the tree. This could also be just y, but often it's better to retain as much of the original data as possible. So this could also be y. And then if we actually got a different value, y, then what we do is that we actually call the toFixedPoint function again recursively. So if there was some kind of change there, then we try to look for further changes in the subtree. And here's this note that the one kind of problem here is this equals function. It can be quite expensive, and also it might be more convenient sometimes to just return sort of a undefined result or nothing result to indicate that no change was made. So that's like another option for doing this. So what this looks like in practice. So here we have this, again, these are just the same two lines for doing the bottom-up transformation. And then there's this fixed point transformation function. And then we have this some sort of data here. This is actually the same data. And what we're doing now here is that we take whatever x we get from the data structure. And if it's a number, and if it's also greater than 0, then we reduce it by 1, and otherwise we return it as is. So what we get here is that all the numbers are reduced to 0 here. This is a kind of silly example, but basically shows what it means. Every time it transforms the data, it just decrements the numbers by 1. We'll see some more interesting examples later. So is this all clear?
So with the fixed point strategy, you are able to make multiple transformation rounds to the same data, and then
Yes.
or actually the intermediate steps of that data until it reaches the fixed point.
Yes.
Why would you do it? Is it a performance thing, or?
It's well, for instance, you can sometimes have like transformations which like reveal new possibilities for transformations. So new redexes, and also sometimes you might happen to have a node for which you can actually apply multiple transformations in sequence. So there might not be like many new locations there, but the same node needs to be transformed with many different rules. So one way to do is to have this toFixedPoint version, which just sort of does that all automatically. So that's kind of the point.
And I guess the paper about the compilers also have this strategy for.
Yes, it discusses it to some length. So
Yeah.
so definitely recommend reading that. Okay, but the idea is probably clear, right? Okay, so so then pattern matching. So this is what I would like to have in JavaScript, or something like this. This is just some kind of imaginary code that I made up. So basically we have this simplify function, which takes some sort of expression, and then it pattern matches on the expression. So if there's a node with a type of sub, and it has a left-hand side and right-hand side, and nothing else, then we actually replace it with this kind of data structure, which is a node with add, which has the same left-hand side, and then right-hand side is the negation of the right-hand side. And then for addition, if the left-hand side and right-hand sides have the same argument, the idea here is that these are like compared for equality. Then if they're if the left-hand side and right side are equal, then it's replaced with a multiplication node by 2. And then if we have this node with which is negation of negation, then we can just cancel out the negations and reduce the return the argument expression. And otherwise, if we don't match any expression, then we can just return the original expression. So one of the points here is that we have these kind of constants here. You cannot have those in destructuring. And then we have variables. You can have those in destructuring expressions also. And also we are doing strict matching. Quite often it's better to be strict in the sense that if you want to match like a sub node which might have some extra data here, like other fields, then you would have to be explicit to capture those with or ignore those with a spread operation. So the idea here is that this would be strict, and then we can have multiple alternatives, like all the alternatives here, and we also have this equality. So those are like kind of basic ideas for pattern matching, and there are many more. Is this idea clear? Cool. So so what we have is this kind of fantasy for doing pattern matching. What we could do now in JavaScript is, for instance, something like this. So we have a function called rule, which takes basically a small description of a pattern matching rule, and then creates a pattern matching replacer from that. So what we have here is that here's the pattern, and here is the replacement, and we're using here like ordinary variables from the JavaScript language, and the idea here is that this left-hand side variable sort of is the same here and here, and also this right-hand side variable is the same in here and here. And the way this the idea here is that the rule function calls this this function with some special values for the left-hand side and right-hand side, so that it can instantiate this pattern, so that it can then analyze it and create a pattern matcher from the special data. And if it matches, then it can call this rule function again with the actual values for the left-hand side and right side match from the data structure, and then instantiate this body that generates the result of the rule. So let's just see how that goes. So here we have actually the complete implementation for this. So here's the rule, and the rule function here takes this rule function now, and then we just instantiate new variables. The variable is just like an empty object. We do this so that we get unique identities for those variables, and we create a variable for every parameter of the rule function. So for instance, here we have 2 parameters, so it would generate 2 variables, and then it calls the rule function with those variables, and then it gets the pattern tongue, and it calls the pattern tongue to instantiate the pattern. So now we have a pattern where the left-hand side and right-hand side positions are replaced with special variables, and then we can so then we actually return this function that takes some data, and in that function we create an environment where we store information about those variables, and then we call this match function, which actually does the pattern matching. We give the environment, the pattern, and the data to that function. So how does the match function work is that it basically recurses on the pattern. So if the pattern is actually a variable, then we check that the data may not be undefined, and also if the environment contains something other than undefined, then it must match the data. And in every case, if everything matches, then it just sets the value of the data to the environment for that pattern. The pattern is the variable, and then it returns true. And if these checks do not pass and the pattern is a variable, then it returns false. So for instance, it might be that there's already something in the environment with a different value, so it doesn't match. And if the pattern is an object, then what we do is that we check that the data must also be an object, and then we look at all the keys in the data must exist in the pattern, otherwise we return false, so that the pattern doesn't match, because we're doing strict matching. And if everything matches there in that way, then we look at all the keys in the pattern, and then we try to match recursively with the same environment and the pattern and data with those matching keys. And if something doesn't match, then we return false, otherwise we return true. And then finally we assume that the pattern is actual literal data that we want to match, and then we just return whether it equals the whether the pattern and data are equal. So, so if this match passes, then what we do is that we actually map all the variables to values that we get from the environment. So here we do the binding. We set the values of the pattern variables to the environment, and in here we extract the values from the environment and get an array of values. Then we call the rule function again with those values, and then we get the replacement tongue, and then we can call the replacement tongue, so we get the new data structure with the replaced values. So what we have here is that we have this rule that transforms a subnode to add and negate, and we can see that it works here. And also if we do some, let's say that of course we can change this, and then if we say change to something different, then we can see that nothing changes here, and so on. So is everything clear until now?
So what was the type for the left-hand side and right-hand side? Are they just the nodes, or was there something special about those?
You mean these?
Yeah.
These, right. So their type is a little bit special in the sense that this rule function here calls the function with different kinds of or different types of things. First, it calls with these variables, which are like special values that it uses to analyze the pattern, and then later it calls the same rule function with actual values, so that it can get the replacement data structure. So you could say that they have like a. So if we were doing this in a typed language, then we could do something like this. We would have like. Actually, for this we would not need to do anything special. We would have like this would be like a variable of some type, and then might be the same type. This might be like an expression in this case, variable of type expression, and then in this replacement case, then here we would actually want to do something a bit special. We would like to do something like, let's say, those variables would be callable, so we could extract the value from the variable here in the body. But because this is untyped language, then we can just have those variables have like two different types. So first we are calling with those special variables, then we're calling with the actual values matched from the data structure.
Can you walk through once on how the environment is built from those? So I was a bit lost there.
All right. So
the
first,
environment is basically just a map, right?
Yeah. In this case, it's just a map.
Yeah, from
So-
variable to value.
Yes.
Yeah.
Yes. So the environment is a mapping from variables to values. So it's like, and we're passing the environment to the matching function. And here in the matching function, we get the environment here. And in all the other cases, I mean, in these cases, we don't touch the environment at all. We just pass it around to the submatching functions, the submatch calls. And then here, in the case of the variable, then we just first we check that data must not be undefined, because we are like assuming that we are actually always dealing with non-undefined values here. And that's kind of for simplicity. You could also do it a little bit differently, but in this case, I've just chosen it this way. And then then we get the existing value for the pattern from the environment. And if it's undefined, then it's okay. It means that the variable hasn't been matched earlier. So then we can just set the value of the pattern to the data, whatever is that at that same position, and return true. Otherwise, if something different from undefined was in the environment already, then we check that the value from the environment is equal to the data, so that they must match in value.
Then it actually sets data back back in again. So
Yeah, but because they're
equal, but
yeah. This could also be optimized so that it won't set it again. And also,
where I'm a bit lost is where does the data come from?
the data comes from here. So basically, this rule returns a function. So here we're creating this subtraction elimination rule, which is a function that takes the data as a parameter and produces the new data. And this is the data here. So this is actually this parameter, when it's called here, is this data structure right here. And then we pass it to the.
Okay. So it's the
Then we pass it.
Yeah. So it's the actual data we're matching against.
Yes.
Yes.
And you didn't implement the spread operation there, so we could have multiple occurrences of an item. Yes.
Yes, that's correct. This doesn't implement, and in fact, it's not implemented in these slides, but there's like a gist of code where it is implemented.
And there's only equals matching, right? So
Yes.
yeah.
So let's see if we would write like we could write for instance like this. So we need to no this. Well, of course, it's generating some undefined data here because we're using left-hand side here. But anyway, now it's checking that these must be equal, otherwise it doesn't do the transformation. Right. More questions?
Yes. It seems like this is kind of related to recursion schemes and like sounds like an anamorphism, like bottom-up transformation. Do you know like what's the kind of why would you use this instead of like a data type which captures the recursion, or is it completely different?
Well, in this case, we basically have this JSON data structure, which is XML. So, and this is also JavaScript. So if this were done in a language where we have this real data types with types, then things might be little bit different.
Okay.
It has to be done differently, but I
But
would say that the underlying ideas are very much the same.
Okay.
It's like a concrete special case of doing those
Okay.
recursion schemes.
How about the like the uniplate? It sounded also like some just recursion transformation. So is it
Yes.
just special case of recursion schemes, or like a fixed point data structure, or
I guess it doesn't actually require a fixed point data structure. And in the uniplate library, there's this idea that you have some sort of data structure where you have certain types of things, and then you can extract those values from the data structure and put replacements back there. And using those, you can create all sorts of recursive procedures for transforming data structures like that. It's quite old. It's like I said, it's like 10 years old at least. So it kind of predates the recursion scheme craze.
Okay.
So, but it's quite interesting paper. I like papers by that guy. So I recommend reading it. It's very readable.
One more note about that. To implement that in other languages, you need, or in that way at least, you need some kind of basic reflection capabilities, right? So,
Or
so
some sort of
checking on the arity of the function.
yeah,
for example.
yeah. You would need something like that,
Yeah.
or some sort of data type generics.
Like 9 variables as well.
And
Mhm.
also the spreading, spreading
Mhm.
of arguments.
or what
Mhm.
do you mean you need? Where do you need?
Well, there was a couple of places where you need like reflective capabilities, so it's.
But
So-
couldn't you have a data type with different, like a sum type? Or
Well,
different
it's
cases?
possible to do many kinds of things. Like you can, if you're using like in a typed language, if you have a function of many parameters, then it's like a curate function, and then you can build combinators with which you can specify as many parameters as you like. So you can do that kind of stuff also there. So, but anyway, let's continue. So one of the ideas is that we need to be able to do like multiple different rules. So here's like this alternatives combinator to which we are giving multiple rules. So if you look at this code here and look at this code, then it's not that bad, I would say. I mean, it's a little bit more verbose, but you can get the basic idea, and it's still a lot more compact than writing if statements. So that's basically a very simple function. So this is like the same code from the previous example, and then there's this alternatives function, which is just this. So it takes multiple functions, and it takes some data x, and then it goes through all the functions, tries to apply the function to the data, and if the result from that is not equal, then it returns it, and if none of the functions return something different, then we just return the original data. So very simple basic idea. So this way we can write multiple alternatives. So now we have like multiple different patterns that we can match here. So if you do add, then if we're adding 3 plus 3, then it replaces it with a multiply. And if we do subtract, then it would replace it at a negate. And if we would have like divide, it would do nothing because there's no rule for divide, and so on. So so now we can describe like a sequence of multiple rules that we want to do. Any questions here? Yeah, this should be quite straightforward. So and then we can use those to do transformations to fixed point. So here's an example. So again, the same code here, and now there's a little bit more interesting example. We have this node which does a subtraction from 3 with the negation of 3. So what happens here is that this actually applies all of those rules, if I'm correct. So basically, first of all, there's this subtraction rule. So this is the first rule. So it replaces with an add and a negate. And then after that, we basically get. Actually, let's see. If I would do this bottom up just, then it would only apply the first one. So we get the add and negate. But then then we could like do the transformation again with the same simplify rule. And now we get the multiply, because then it's doing bottom up, then it actually folds the remaining things there. But the to fix point does just that kind of automatically for us, so we don't have to think about the order in which the transformations are done. So any questions here?
So the order of the rules doesn't matter in this case?
In this case, it doesn't matter because the rules are disjoint. So basically, they all match different patterns. So if it would be the case that they might match the same data, then the order would matter. So it's actually that's a very good question actually. So it's in practice it's often useful to be able to have the rules such that they don't match the same data, because then you can have some sort of interesting cases where you don't know what's going on. Other questions? All right, so that's pretty straightforward. So there's a lot of room for improvement here. So first of all, this is quite inefficient. So if you look at the code, then it actually examines the pattern over and over again. So the rule function, every time it's applied, then it goes through the pattern again to analyze the pattern. And it also does other inefficient things, like the variables are stored in a hash map, and it would actually be possible to sort of replace the variables with integers, like 0, 1, 2, and 3, and so on, and then use an array. That's also possible. In my actual implementation, I do it like that. It's also inexpressive, so there are no spread patterns, and then there could be like or and not patterns, and there could be predicate patterns and many other kinds of things. It's also not modular, so basically we have this one big match function which does everything. So every time we add something new, then we would go to that match function. And also in our actual implementation, we had other things operating on patterns, like a pretty printer for debugging purposes, and maybe something different also. But you could have many kinds of things, like something you could, for instance, like sometimes perform checks on the patterns that they make sense. You might have different function for analyzing the patterns for that and so on. So you wouldn't want to make it so that every time you add a new kind of pattern, then you would have to modify all of those functions. It would be nice if you could do it more modularly. And also it's a little bit verbose, so sometimes the chunks are not needed. So those can be eliminated sometimes. But let's look at a simple way to improve the efficiency. So this is like a very, very basic functional programming technique called staging. So what we had earlier is this kind of function that takes an environment, pattern, and data all at the same time. But and the problem with this is that when we write like this, then the pattern has to be analyzed every time again. So if we would change it like this, that we first have a function that returns takes a pattern and then returns a function from the environment and data, then we can actually pre-process the pattern here. So what this looks like in practice.
So what's called staging?
Staging is this. This is a staged function. It has multiple stages. Like this has only one stage. You can apply with only these 3 arguments, and then it does something. And in this case, you can first apply it with the pattern argument, and that's like the first stage. Then it does something, and then you can apply more arguments, and then it does more things. So that's like the second stage. So that's staging. So so this is like only a small modification to the original code. We have this. So first of all, in here, when we instantiate the pattern, we call the rule function and we get the pattern chunk. And then we call this to match at this point before we get the data, and then we get the matcher function. And the to match now takes this pattern, and if it's a variable pattern, then it actually returns this function that does the matching for the variable. And if it's an object, then it actually goes and maps through all the patterns in the pattern object to create matchers, so that they can use those matchers instead of analyzing the pattern here again. And in the last case, it returns this equality function. So now we actually get like a more efficient function for doing pattern matching. We no longer need to analyze the pattern every time we try to match something. So is the idea here clear? Questions?
Is the original match function recursive?
Yes, and this one is also this also calls match here.
Yes. Yeah.
You're running out of time a bit.
Right.
Like 5 minutes.
Okay. Actually, not that much. Yeah. Right. So maybe I'll go through the whole presentation still. So how would we improve modularity? So we could do something like this. We could split the matcher to these like handlers for different features. So we have this function is, which takes a pattern and returns whether this is handled by the handler, and to match function, which takes the pattern and like the whole matcher function, and then returns a matcher. So then at the end we could just say that these are the handlers that we want to combine, and then we can have this to match function which takes a pattern and then it tries to find a handler, and if it doesn't find a handler, then it's an error, but usually we would find a handler and then we'd call the to match function from the handler. So how does this look like? Just briefly in the background, it's like this. We have the variable here, and then we have the variable handler. So this is like all the code except for those environments that's required for handling variables. And then here's this part that handling objects, and then is here. This is the part that handles constants, and then we can make a list of all those handlers, and then we have the too much function here, and now we have sort of a compositional way to create these pattern matchings. So now if we would add different kinds of patterns, like OR patterns and patterns and so on, then we would only like implement this kind of independent chunk of code and then add it to the list of handlers, and then instead of like modifying possibly multiple different functions. And this really has a kind of nice effect. I actually wasn't originally writing the actual pattern matcher like this. I was writing it with these functions that did this analysis on the pattern, and now and then I later refactored it to work like this. And it's really nice that after that I added many more features to the pattern matcher. So all the diffs for like a block of code here and then one change there, and they were very simple changes instead of like shotgun changes where you're modifying multiple places in the code. Right, so of course because of the time limits so how do you actually go to the final the actual implementation? I have this gist here which has the actual pattern matcher. This does features like the spread patterns and OR and so on. And as you can see, it's implemented here like these handler things, and that's all the basic patterns. I think you should be able to follow this code fairly easily. And this also has other kinds of features. It's like has debugging features. So every time this matches patterns, then it actually records information whether something was matched or not. And then at the end of the program, we can print out which patterns did not match any times and so on. So those can be quite useful for debugging. So I'll put these slides somewhere public, so you will be able to find the gist. So what would be like the pros and cons of this approach? I think that pattern matching based rules are fairly easy to understand, much easier to understand than sort of traditional code using if and else statements or switch cases. And also one of the nice things about this is that you don't kind of manually need to traverse the XML tree. On the other hand, one problem is that it can be difficult to understand why something doesn't match. You have the rule and you have the data, and you're trying to figure out why isn't it transforming something. And usually it's like there's a bug in the pattern, but where is the bug and why it's not matching? So those can be kind of puzzling sometimes. And also because this is like just like we have this existing huge XML structure, and then we are like doing transformations here and there. So how do you know that it's actually done everything like the way we want it? So that's like a difficulty. So I would say that when we started doing this, and I wasn't actually really working on this first, but in retrospect, I would do things slightly differently now. I would probably just implement the pattern matcher, and then instead of doing the bottom-up rewriting, then I would actually just write a recursive function that kind of matches the XML, the input HTML structure, and then produces the output XML structure. So that way, it's very easy to understand where you're going in the data structure and understand why something doesn't match. So that's like a little bit more verbose and more explicit way, but then it's much easier to debug, I think.
I guess there's a chance also to have if you use fixed points to have the system oscillate.
Yes, it's possible to go into a loop, and there's actually also a feature in the actual matcher that limits the number of transformations that can be done. So you can actually like limit every pattern that you want, and there's like a global limit also.
Yeah.
But it's actually those are like fairly easy to debug, but what's kind of puzzling sometimes is that you have the pattern and because the XML data structure is so complex, so it's not very easy to see why some pattern doesn't match. So that was like a real problem. You have the pattern and it looks like it should match, and then it doesn't match, and then you need to figure out why it doesn't match.
Are there any valid cases where it oscillates between two versions basically of the tree? It sounds like it's kind of arbitrary then where you end up if you set up hard limits.
That's basically for debugging only. So
Okay.
the limits are like you run the program, and then if
So
it
like
hits
if
the
you
limit,
get
then
set, there's like something wrong in one of the rules, I guess.
usually the idea is that if the limit is reached, then it's an error. So it probably throws an exception in that case, probably. So I'll probably find some links here, but there's like a description of some sort of pattern matching in this structure and interpretation of computer programs book, and there are lots of at least a couple of papers on pattern matching combinator libraries for type languages. Of course, recursion schemes are related. We didn't actually talk about prettier printer here at all, but it was used like in the actual matcher to print out this debug information. Also, the idea of doing the modular pattern matcher is basically the same as the expression problem or the modular interpreter problem, and the idea of using those ordinary functions, ordinary variables, to actually build the pattern and the replacement is like a very simple example of high order abstract syntax. So those are all interesting stuff
These
to
are
read
good
about.
suggestions for further topics, I think.
Yeah.
Okay, so last time that I checked, there was at least one pattern matching library already in JavaScript. So is this better, or how you have made your own?
Of course, it's better.
And there was, I think there was some kind of pull request or suggestion to include to ECMAScript the pattern matching.
Yeah, that's quite true.
Yeah.
Yeah.
Proposal, yeah.
That's actually quite a question. So one of the reasons, actually originally, this started out as using there's like a pattern matcher feature in the Lens library. So originally the rules used that one, but it's more limited. So that was like one reason for building another pattern matcher. And also I would guess that the pattern matching feature that's perhaps coming to JavaScript at some point, it will also be more limited. It probably doesn't have equality, for instance. It probably might not have like all the and or and not patterns and so on. And one of the patterns that we did use at least at some point is to be able to like say that we have this data structure and then we might want to match somewhere inside this kind of pattern. So that's also quite complex pattern, and those are very easy to implement in their own pattern matcher, but probably won't find those in the language level pattern matcher. And also so those are like the basic reasons, like the expressibility and also the debuggability. Those are like the features for which we wrote our own.
Okay, we need to move on.
Yeah.
Where we can find this?